In this video, we're going to start Chapter 6 of the trigonometry textbook. Chapter 6, you can see, is on inverse trig functions and trigonometric equations. So it says inverse circular functions, but as I've mentioned, when we see this term circular function, we're just going to think of a trig function in radians. If you want more specifics on what I'm referring to there, then go back to Chapter 3, where we talked about circular functions and what all that means. Okay, so in this video, we're going to go through the opening section, which is on the inverse trig functions, and then the next two sections are on trigonometric equations. So we learned how to solve different types of equations in algebra: linear equations, quadratic equations, logarithmic, exponential, absolute value equations. However, in algebra, we never worked with trig functions. We learned about all the other types of fundamental functions that we use in math: logarithmic functions, polynomial functions, etc. And so we learned how to solve equations with those types of expressions. But in trigonometry, we were introduced to the trigonometric functions, so it makes sense that we're going to need to learn how to solve equations that involve trig functions. Okay, and then in the final section of this chapter, we're going to look at equations that involve inverse trig functions. But first, we need to learn about exactly what an inverse trig function is. And that's what we're going to do in this video. All right, so here's the opening picture for this chapter. It says sound waves, such as those initiated by musical instruments, travel in sinusoidal patterns that can be graphed as sine or cosine functions and described by trigonometric equations. So, once again, I'm not sure what they're referring to as that's so specific to this chapter, but yeah, sound waves, any kind of purely natural, periodic, something that's varying periodically, a water wave, a sound wave, anything that's, sound waves are vibrations, right? It's periodic, that's going to be sinusoidal. Electromagnetic waves, sinusoidal. Okay, now just to point out, we have up to this point, before this chapter, we have kind of looked at inverse trig functions. So there were some problems where we used this inverse notation here to solve for angles. Like, we didn't know the angle in a problem, and we had to solve for the angle. So we have used these inverse operations before this chapter. The idea of we know what a trig function value of an angle is equal to. So what is that angle, though? We know what the trig function is equal to, but what's the angle that resulted in that value? We've used the calculator to figure that out prior to this chapter. However, now we're going to look at this operation more officially. Okay, so this section starts with a review of the idea of what an inverse function is. And we go through this in full detail, all of these concepts in algebra. And so what I'll do is I'll include it in the trigonometry playlist. I'll put it just before this video will be, so you might, if you're following along in the course in sequence, you might have already watched those videos, but I'll include those inverse function videos from algebra in this playlist. So we're not going to go through all of this here. It talks about, it reviews what exactly is a function. Then what's the domain and range of a function? What is a one-to-one function? The horizontal line test, that tests to see if a function is one-to-one. What exactly does an inverse mean? And how do you calculate an inverse? So we're not going to go through all that here. I will just watch, if you need a review, watch those videos from the algebra playlist. Okay, but the main idea here, though, of what we're trying to calculate or determine when it comes to these inverse functions, the inverse trig functions, is, so remember the basic idea of an inverse is, so we start with just like a variable. Nothing's been done to it. Okay, if we perform an operation on it based on any of the operations on variables that we've learned in algebra and in trigonometry, those operations are the trig functions. But so let's say we apply the cube operation to this. We cube it. Well, the inverse function of that operation, or the inverse operation, is whatever would undo what we just did here and get us back to what we started with x. So the inverse of cubing something is taking the cube root. And then we're back where we started. We undid the first operation. And the way that inverses work is that an inverse you have an inverse operation is they're inverses of each other. So you could always go in you could look at it from the other perspective. You could say start with x and apply the cube root operation to it. Now if we want to undo what we did here, we put that into the cube operation and we're back where we started. Okay? So that's what we're developing here. That's the idea of an inverse trig function. We're starting with a variable x or theta, and we already defined clearly what all of the trig function operations are. It's the same idea. Like instead of cubing x or taking the log of x, it's just we're saying, okay, what is the sine of x? We've applied like an operation to the variable. And so now we want to think about, well, okay, if we want to undo what we just did, then what do we need to put this sine of x into, what function, to where we get x back? And that's what the inverse is. And the notation is going to be, we would put sine of x into the inverse, and we would get x back. So that's the notation for an inverse of a trig function. Inverse sine is going to be sine to the minus 1. We learned this before. Sine to the minus 1, cosine to the minus 1. Okay, but the same idea in that you could go the opposite direction for when it comes to trig functions going either, or inverse functions going either direction. We could start with the variable x and apply the inverse operation to it. And now if we wanted to undo this, we would, the inverse of the inverse sine is just the sine itself. And we would be back at x. Okay, so that's the idea. That's what we're trying to develop in this section. We want to look at, for example, with exponentials, you had b to the x. That's what you started with. And then the inverse of this is log base b of x. Okay, those are inverse operations. Well, it's kind of like we've already defined the trig functions. So that's kind of like, imagine that's like the b to the x. We know all of the trig functions. Okay, now we want to look at, well, what are the inverses? What's the properties of the inverses? What's the graphs of the inverses look like? What's the domain and range? We want to analyze the inverses, just like we did with the regular functions. Okay, now the inverses, though, like we just have to make up math is going to make up a notation. So when it came to, you had b to the x, and they could have written the inverse however they want. They chose this log base b of x for some reason. Okay, well, the notation for the inverse is, the way they defined it, is going to be this. Etc. You put this minus 1 here. Now, we've talked about this before, but it's important to note that this can be confusing, this notation, because if we had something like cosine, if we had this, well, we know that this means cosine of x squared. However, with inverses, cosine this does not equal to, that would be the reciprocal 1 over cosine x. So that would be secant x. This is secant x. No, absolutely not. Yes, this is equal to secant x, but cosine to x to the minus 1 is equal to secant x, but most certainly all of that is not equal to this. Not at all. So that is confusing, and that's just the way it is. You could write cosine to the b of x, as long as b isn't equal to -1. I think maybe you could even do b being equal to 0. I want to say you could say that cosine of the 0x is equal to cosine of x to the 0, which is equal to 1, assuming cosine x isn't equal to 0, because 0 to the 0 is undefined. But I want to say you could say cosine of the 0 like that, but like the idea is you could say a trig function to any power, any real number, positive, negative. This could be cosine. So cosine to the minus pi of x would be 1 over cosine x to the pi. I believe you can do this. You could take, so this is equal to cosine of x to the b as long as b is not equal to -1, because the -1 is reserved for the notation for inverse of the trig function. And so if you want to write the reciprocal of a trig function, you just have to do it like this. There's no way you can't use that other notation. So you have to keep that in mind. Okay, so we're starting with the inverse sine function. We want to come up with an official definition for the inverse sine function. We know the basics of how it's supposed to operate. So again, prior to this chapter, we've used these functions here. We get the idea. We have a value that we know, for example, is the tangent of an angle. We have the value. We want to know what that what is the angle that value corresponds to. And we've used these functions before, so we get the idea of what their purpose is, but now we want to define them more officially. So how are we going to define the sine function officially, the inverse sine function? Well, okay. Let me bring this in here. Okay, it says refer to the graph of the sine function in figure 4 or on the next page. So here's that figure. So applying the horizontal line test, we see that sine of x does not define a one-to-one function. So yeah, if you think about all of the trig function graphs that we did in chapter 4, they're all called trig functions. They have the name function. So all of those pass the vertical line test. They're all functions. However, if you think about it, none of those pass the horizontal line test. None, because they're all periodic. The pattern repeats over and over again to infinity. And for a function to be one-to-one, you can't have multiple or separate inputs mapping to the same output. Well, if you have a periodic function, then it's 100% not going to be one-to-one, because you have multiple inputs repeating the same output over and over again up and down the x-axis. So none of the trig functions are one-to-one. And that's an issue when it comes to for inverses, because for a function to have an inverse, it needs to be one-to-one. Or let me restate that. For a function to have an inverse function, it needs to be one-to-one. You can take the inverse of any relation. All relations, if they're a function or not, have an inverse. You just flip the outputs from you flip from the to where the outputs become the inputs and the inputs become the outputs. You just flip it, right? So any relation, no matter what it is, function or not, has an inverse. But we're talking about for it to be an inverse function. So if a function isn't one-to-one, then it doesn't have an inverse function. And we're trying to define the inverse trig functions. Right now we're trying to define the inverse sine function. So now what we talked about, though, is that one way to make something one-to-one is to restrict the domain. And so that's what we're going to do with the trig functions to define the inverses. We're going to restrict the domain. Okay. So now if you think about it, what do we need to, how much of starting with the sine function do we need to restrict? Do we need to kind of like rope off in order to do this? You might say, well, okay, probably one period. Well, actually, one period would be too much. All we're going to need to rope off is just the exact amount to where we've covered the full range of the sine function. So all the outputs. So we know sine goes from -1 to 1. So we need to just rope off to where we cover every single possible value going from output value going from -1 to 1. no more to where we want to go the largest amount to where we don't repeat that same y value. Okay, and we're going to choose. We can choose that there's an infinite number of x intervals to where that's the case because it's repeats. It's a periodic function, but we're going to choose the simplest possible. So if we think about the sine function, if we go from x is equal to minus pi over 2 to pi over 2, then we go from -1 all the way to 1, that full range. And so that's what we're gonna say, that we're taking the inverse, not of the sine function, but of the sine function with domain restricted to minus pi over 2 to pi over 2, including the endpoints. This is not a one-to-one function. However, this is a one-to-one function. So this has an inverse function. And, again, why are we roping off an area that covers the full range of sine? Well, think about the goal here. The goal is that we're trying to define a function to where we input the values of the that's going to be input into this inverse sine function is any of the possible values that sine results in. That's the idea. We have a value that it was the sine of some angle. We have that value, and we want to figure out what was that angle that corresponded to that. Okay, well, what are the possible outputs of the sine function? It's an infinite number of values that anything between -1 and 1, including the endpoints. And so that's what we've restricted the sine function, the domain, to where we include every single possible output of sine, but it's never repeated. Like there's never, but we haven't created the banding too large to where that y output value is repeated more than one time. And now you might also be thinking, well, wait a minute, how come that wouldn't be a full period? Why is it half of a period? Well, because what makes a full period is that you go from 0 to 1 going up, then from 1 to 0 going down. So when it comes to the periodic nature, these two regions are different. However, when it comes to just mapping out strictly the domain or the range one time, well, when you go from up to 1 or down to 1, in that context, these are the same. So this is redundant. But when it comes to what the period is, well, here you have a function that's increasing going from 0 to 1. Here it's decreasing going from 1 to 0. So that's kind of part of the period. Okay. So, all right. So now let's take the inverse of this. So let's come to the next page. All right. So once again, we've got y is equal to sine of x over the interval. So we're going to include the endpoints, right? Because the endpoints at minus pi over 2, or sine of x is equal to -1. That's part of the range of sine. Like if we didn't include the endpoints, then we wouldn't be including 1 and -1, which is part of the range of sine. So we include the endpoints. Okay. Now, how do we get the inverse of this? Well, we learned in algebra how to find the inverse of a function. What we do is we start by switching the x and the y. Okay, then we solve for y. And how do we solve for y? Well, we have the sine of y. We want to undo this. We want to isolate the y. How do we undo this? Well, we use the inverse. So we're going to take the inverse sine of both sides. Okay, now this undoes. I'll bring that over here. This isolates the y. And then in algebra, we would then change the y to the inverse function notation. But we can just leave it like this. And there you go. There's the inverse function. Now, so I'll leave it with just the y. Now, we we learned in algebra that, so what's the domain and range of this? The domain is going to, that's going to be, so here, with the sine function, here's the domain, and then the range we know is right of the sine function with this domain restriction, its range is -1 to 1. But when we do the inverse, now the domain is going to be whatever the range was, which makes sense, and the range is going to be what the domain was. The domain, you can't input something that's less than -1 or greater than 1. That wouldn't make any sense. You're saying, have this value, there was an angle, and that angle was you took the sine of that angle and you got something. I have that something. I want to know what that angle was. That something is going to be between -1 and 1. If it's not, that doesn't make any sense. Okay? And then the range, though, the outputs of the inverse trig function, when you think about the general definition of the trig functions, the output is infinite, because it could be, we're asking, we have a value, like let's say we have 1/4. We got this value. We know that the sine of an angle was taken and we got 1/4. We want to know what is that, what angle was applied to the sine to get 1/4. Well, technically it's going to be, is an infinite number of angles, because it's going to be, you can have an angle and all of its coterminal angles would satisfy that criteria. However, we have applied the restriction to where we're only looking at, when it comes to the general definition, okay, when it comes to for inverse sine, we're strictly thinking about the angles that go from -π/2 to π/2. That covers the full range of sine. So when you say the inverse sine, you're asking, okay, what angle does this correspond to? It's going to give you, since this covers the full range, right? The full range of sine, it's going to give you an angle between -π/2 and π/2. So, and it's going to be one unique angle, because there's only, between -π/2 and π/2, there's only one angle where if you took the sine of that angle, it's going to give you +1/4. And that's what the inverse sine is going to give you. Okay? So now, next it notes, so yeah, we can, there's another way to say inverses. We can say arc, use arc. So you could say sine to the -1 of x, or arc sine of x, or arc cosine, arc tangent. That means the same thing. So sine, that is equal to arc, same thing. You can pick whatever you want. Okay. Now, when it comes to the graph of inverse sine, well, we know that so here's the sine function with restricted domain that we just found the inverse of. To get its graph, we flip it about y is equal to x. Flip this. But that's kind of hard to see here because these scales are different. So let me bring in a graph from Desmos. Okay, so yeah, this is easier to, the scales are the same here. So in blue is sine x with the domain, the sine x with the domain from -π/2 to π/2 inclusive. So you can see it's that sine curve if you continued on. Okay, and the red is arc sine, and that it's just flipped about y is equal to x, right? It's flipped. Okay, it's kind of hard to see that here because I don't think they have it scaled evenly. But yeah, I mean that's the graph of the inverse sine. That's it. It's just this here with this domain restriction flipped about y is equal to x, and so it's going to be just like this. It's going to be continuous, smooth curve with the domain and range flipped. The domain and range of this flipped. And there you go. That is the inverse sine function. Y is equal to sine of -1 of x, or y is equal to arc sine of x, means that x is equal to sine of y. It's saying that you're solving for an angle. Sine of that angle equals what you inputted into the inverse sine. And the y is going to be, the angle is going to be something between minus pi over 2 and pi over 2. Now, you can note, though, that yes, that is the technical definition of the inverse sine is based on that restriction. It's only going to give you those angles between minus pi over 2 and pi over 2. But this is where it can get a little confusing. When you're applying an inverse trig function, you're going to get an output. It's going to give you an output, and you're still going to be thinking about all of the other potential values that would satisfy the equation you're dealing with. And so why is that? Well, because, so if we come here, so let's solve this y is equal to arc sine of 1/2. Well, I mean, we're not solving anything. We're just saying, okay, what is arc sine of 1/2? So, okay, we're thinking about, this is the arc sine function. So it's what angle, when you take the sine of a certain angle, you're going to get 1/2. What angle is that? Well, we know the inverse sine function is, it's only going to give you angles between minus pi over 2 and pi over 2, or negative 90 to 90, whatever. Okay. And so in that case, we know that sine is positive in quadrant 1, negative in quadrant 4. So we know we're going to be somewhere in quadrant 1. Okay. So we're looking for, what is this angle theta? Okay. And so the sine of this angle is opposite over hypotenuse. So we're going to have 1 over 2. All right. Now, do we need to put this into our calculator, or can we do this manually? If we think about the reference 30, 60, 90, 45, 45, 90 triangles, well, yeah, I think the 30, 60, 90 will work here. So let's see. 1 root 3, 2. So sine of 30 is 1 over 2. And so there you go. This is 30 degrees, or we can convert that to radians, and that would be, so 180 degrees for every pi radians. So 30 degrees is pi over 6 radians, so this is going to be equal to pi over 6. That is the one and only one output to arc sine of 1/2 is pi over 6. That is it, 100%. The only this is the one and only answer. However, if you think about it, I might not have said this correctly in the beginning of this video, but it's not that there are going to be, so if we're wondering what angle, when you take the sine of that angle, you get 1/2. Well, it's going to be 30 degrees, and every angle coterminal with 30 degrees. That is true. But I might not have mentioned this correctly before, but it's actually, if you think about it, it's more than that, though. It's really going to be, so sine is positive in quadrant 1 and quadrant 2. If you've got whatever angle is coterminal, or not coterminal, whatever angle has reference angle 30 degrees, as so that would be what? Over here, that would be 150. This would be 150. The sine of 150 is also going to be equal to 1/2. Sine is positive in quadrant 2. And so what technically satisfies it doesn't satisfy this function, it satisfies the question that this function is asking in terms of what angle, when you take the sine of that angle, you get positive 1/2. That's going to be, the answer to that question is any angle that is coterminal with 30 degrees or coterminal with 150 degrees, including obviously 30 and 150. And so the inverse sine function, when it comes to like real life problems, you kind of use it as a tool. It's going to give you understand what the inverse sine function means. Okay. You understand what it's going to output. You understand its domain and range. And so you just use it as a tool. It's going to give you that angle. It's going to give you an angle. And then from there, okay, well, you can figure out, all right, what would be the corresponding trig function in another quadrant that would give me this same value? It's going to have the same reference angle. You could figure that out, right? It doesn't have to be a special angle. You could figure it out that, here this is a positive value for sine. So okay, this trig function is, where all the trig functions are positive or negative, the quadrants, and you could figure out, okay, here are the two angles that would, within 0 to 360, that would satisfy this, and then any angle coterminal with that, and it would just be based, you'd have to look at the specifics of the problem you're dealing with. You'd understand your problem to know whether or not you need to use 150 or 30. Like, in other words, it might be the case where you're solving an equation, where we're going to talk about this, you're solving an equation with an inverse trig function or whatnot, and you get out pi over 6. But the answer to the problem is going to be, or 30 degrees, the answer to the problem is going to be 150. That is absolutely happens all the time. But it's just that in order to define the inverse sine function, the inverse trig functions, we're not going to have multiple outputs corresponding to the same input. Then it would be a function. Okay. What about inverse sine of -1? Well, okay, what value when you take what angle when you take its sine do you get -1? And we're just thinking about potential angles between minus pi over 2 and pi over 2. Well, that would be when the y value is equal to the radius, but in the negative direction. So that's this. So minus pi over 2. Okay. What about the inverse sine of -2? Well, that has no solution. It does not exist. That's outside of there's no value here. If we come between minus the full range of sine minus pi over 2 over 2, there's no angle you can input into sine and get out -2. This is outside of you can't input this into the inverse sine. That's outside of the domain of inverse sine. So no solution. That's the way you think about it. It's kind of like you input, and it's like you input into log a negative number. That's outside of the domain. No solution. Same thing with this. Okay, so here it says in example 1b, it is tempting to give the value of the inverse sine of -1 as 3 pi over 2. Yeah, because if we know that the inverse sine of -1 is it's this negative vertical. It's the negative vertical, right? That's whenever the radius is equal to the y value in the negative direction, that's the negative vertical. All right, well, we know that's 3 pi over 2. So we can put 3 pi over 2, but that's incorrect. That is incorrect. That's not the definition of the inverse sine function. It goes from minus pi over 2 to pi over 2. Now, it is, however, true, though, when you think about the question that the inverse sine is asking, then yes, 3 pi over 2 is an answer to that question. But as far as the literal inverse sine function, how it's programmed into calculators and computers and the inverse sine itself, the range is minus pi over 2 to pi over 2. That's it. Once you have the value that the inverse sine gives you, then you can go ahead and think about, okay, what other angles would actually satisfy this criteria of if I took the sine of this angle, I would get -1. In that case, it would be any angle that's coterminal with minus 90 degrees. And in that case, it would just be, there's only one angle. Here there was two separate angles that resulted in two separate angles within the 0 to 360 that created 1/2, but with a quadrantal angle, it's just going to be one angle from 0 to 360 that satisfies it. Okay, now, so here's a summary of the inverse sine function. Domain -1 to 1, range minus pi over 2 to pi over 2. It's continuous. It's always increasing, and it has one x-intercept, one y-intercept, both at the origin. Okay, and then also it has a symmetry. It's symmetric with respect to the origin. we're going to see actually like inverse cosine doesn't have any symmetry. So it's an odd function. The inverse sine of minus x is equal to minus inverse sine of x. All right, we'll finish this section in the next video.